Now let's talk about this MIPS support for the interrupt and exception. Again, we'll not do any like hands-on programming or things like that. It is just a theoretical discussion and just to kind of for your information kind of slides where you basically need to know like what MIPS supports, and maybe in the operating system we'll pick up one specific example, maybe MIPS, may not be MIPS, to study the interrupt service system, interrupt system in detail. So interrupt, first of all, for MIPS, interrupt transfer to the to this address. This is the fixed address where interrupt, if first any interrupt comes in, your program counter is updated to have this have this address, means you are jumping to that location 8000 180. So remember, this is a 7 digit. So on the 8 digit 32 bit code, it would be 0800 right, 0800 Okay, so just to note, this is at 7. This is typed in the slide as a 7 digit hex. Now, interrupt service is handled by a parallel processor with respect to the generic processor that we described. It's in the MIPS or MARS, is called Coprocessor 0. But unlike Coprocessor 1, which is floating point processor, which usually resides outside of the processor, the coprocessor 0 is usually part of the CPU and store information for program to handle interrupts. It's from complexity wise and size wise is a smaller footprint than the original generic processor MIPS, but it is a processor and it has capability to run in parallel with the main generic processor. This processor, coprocessor 0, contains several registers to store values. Your simulation environment in Mars, which is underlying it is running SPIM, provides only a part of it. So whatever you see in the Mars window in the coprocessor register list, they're just the part that simulator provides, not the full list that real MIPS coprocessor 0 supports. And these can be read or write using MFC 0 and MTC 0. Like it's similar to MF low, MF high kind of concept. It is move from coprocessor 0, move to coprocessor 0 instruction. Now, coprocessor registers, there are a couple of example and register number and their usage. Bad V address is a register which basically tells memory address at which appending memory reference occurs. It's used for your misaligned memory access interrupt, for example. Count is a counter timer. It's basically used by operating system to time slice your program execution. So remember, like our computing operating system provide kind of a parallel execution environment where apparently multiple applications goes in parallel, right? In your system, you open your browser, you open your Mars IDE, you open up your text editor, and so on and so forth. Everything seems like it's those 3-4 processes or applications goes in parallel, but in a sense, let's say if your system has only one processor, your operating system's time slice the usage of the processor and divide those slices through these 4 applications, whichever is running in parallel. So in fact, these 4 applications are not truly running in parallel. Like each of them get some fair share of the processor time and go into something called sleep state, and each process, each application enjoys a specific amount of time before it goes to the sleep, and then there it wait for next turn to be executed in the processor. So this count is used as a timer, which basically operating system sets when it schedule that application to the processor to be get executed, and after this counting is done, then it stop that process, okay, make it into the sleep state and bring up another next process in the queue alive to be executed inside the processor. So detail would be in your operating system class. There are many scheduling algorithms to be learned and so on and so forth. But on the hardware side, this time slicing needs to have a support to the operating system, and count is that register. Okay. And compare is value compared against a timer that cause interrupt. So basically counter counts, and then compare register contents. Okay, how much time it's allocated for this process or this application. If once they match together, then one interrupt comes in. Then status, basically we'll talk about this in detail, status and cause in next slide. They are basically used for interrupt mask implementation and enable bits, and cause is basically gives some idea about exception types and pending interrupt bits, if any. EPC is the address of the instruction that caused the exception. Basically, this is needed to go back to the point to user program resumption, right? To resume the user program. And config register is for configuration of the machine. Well, we'll not touch more on that. Now about this cause and status registers. These two are important, and let's look a little bit detail about this thing. Your cause, like status register, is basically some of the bits are used as an interrupt masking. What does it mean? Is that as long as this, so each bit, by the way, corresponds to one device, one peripheral device attached. Okay, so in this example, 8 bits are allocated for supporting 8 peripheral device, and if they are all 1, that means any one of them can make an interrupt. Okay, is allowed. Now let's say one of the bit becomes 0, that means these bits, that corresponding device is disallowed, is not allowed to send an interrupt. All right. So this set of bits basically enables to have implement a priority in the interrupt routine. Let's say higher priority, let's say MSB side is the higher priority devices and LSB side is a lower priority devices. So that means, let's say bit number 0, 1, bit 8, 9, 10, 11th bit is 11th, that corresponding device is creating an interrupt and service routine is going on. At that point, what operating system will do, it will make the 11, 10, 9, 8, these 4 bit at 0, but it will keep the 12, 13, 14, 15, those other bits as 1. So it is implementing an hierarchy or priority list of the devices. Means the devices corresponding to this higher bit can still interrupt this machine while an interrupt service routine is being executed for the device connected corresponding to the bit 11. But the lower bits, devices corresponding to the lower bits, like bit starting from bit 11, 11, 10, 9, 8, those devices can no longer send an interrupt. Those interrupt won't be, okay, let me rephrase. They can send an interrupt, but system will not stop current interrupt routine to serve them. Okay, that's what it means. So that means if some lower priority device interrupt in between the interrupt service routine execution, that means there should be some mechanism to say that, hey, there is some pending interrupt to be looked at. Okay, this is what is done through the cause register, where we have same number of bits, like 8 to 15 bits, and it is 0 to start with, but if there is a pending, means it's in the queue, those corresponding bit will turn to 1. So let's say lower priority device sends an interrupt while the higher priority interrupt service routine is going on. So corresponding bit in the cause register of that device will turn to 1. So that operating system knows after coming back from the interrupt service routine that there are some more interrupt to be addressed. Okay. And there are some bit in the cause register is called exception code, which is prefixed, fixed per device. So when you load the device driver and everything, this gets settled up with the operating system, and operating system knows what are these exception codes, right? So different exception codes are allotted for different devices, and corresponding like messages, actions, etc. all are part of your device driver routine are registered in the operating system. Now come back to the status register. User mode, this one of the bits says whether I am in a kernel mode or a user program mode, and based on that some priority levels gets assigned. And then this interrupt enable signal is another of the interest. If it is turned to 0, that means all the interrupt are disabled, no matter what the interrupt mask says. Okay, if it is making 0, then it is interrupt is disabled completely from the system. Or if it is turned to 1, it's become interrupt enable. So usually some sensitive routines in the operating system turns off the interrupt before it goes and make those execute those routines. So hopefully in operating system again you'll see these things and study about that. And what happens during interrupt is disabled, your pending interrupts bits still get updated, so that after operating system done with those critical operations, then it can look at into this cause register to check if there are any pending interrupts and to be serviced at that point. About some cause codes, just an example. For example, like an number 4 or 5, it's basically address error exception for store and for load and store, and maybe breakpoint is for 9 is for breakpoint. Is basically your debugging facility. syscall is 8. You are familiar with the syscall operation. And arithmetic overflow exception, right? This is caused by 12. Floating point exception is 15. Trap is another type of exception, is called 13. So these are a couple of examples of the call code, and again details conception should be discussed in your operating system class. So that's all for this lecture 22. If you have any questions, send me email or update in the discussion or ask me in class.